using Newton's second law. I modeled it being thrown down through its bounce to show the conservation of energy. And so this is my problem statement. And then the principles that I used were Newton's second law, specifically force equals mass times velocity. And this was used to model the motion and find the velocity later on in the code. And then the other principle used was the energy principle, specifically delta E equals delta W plus delta Q, which is the internal energy. And so this had to be found for when the ball hits the ground. So the final result was that energy is transferred into internal energy when the ball bounces and compresses against the floor slightly, meaning energy is still conserved. So this is the video of my ball bouncing. So the calibration stick I used was the height of my friend, and then I tracked the motion of the ball once it left her hand and bounced. And so over here on the position you can see that because of the initial force, the ball reaches about the same height as it would normally, suggesting that there's no energy transfer. However, because of the difference in velocities there's obviously some change in initial velocity that has to be addressed. So the concepts I used, like I said earlier, were Newton's second law. And so in order to do this, an assumption I made was that the F net is the gravitational force only. And this is because even though some drag could exist, it caused a huge underprediction in my model, which makes sense because the basketball was heavy enough and thrown with enough force that drag shouldn't have a huge effect. So I used acceleration equals F net divided by mass, or Newton's second law, in order to find the velocity using this part of Newton's second law, and then also update the position in order to properly track the ball. And so then I used the energy principle in order to properly model the bounce of the ball. So I used delta E equals delta W plus delta Q, and basically the concept that delta Q equals negative delta W, because there's no energy transferred into the system of the ball, it's just converted into internal energy. So this is my code. I initialized using this line where I made basically a model of the ground so that the ball would bounce properly. And then I set where the ground was equal to the Y position where the ball hits the ground in tracker. And then I calculated the initial velocity by doing the change in position divided by change in time for once the ball left her hand, because it was thrown down, not just dropped. And this is the mass of the ball. And so I created a CSV file to output the position data so that I could compare it in my model. So I used this while loop to advance the velocity and position. So I set up to find the kinetic energy and the gravitational potential energy, which I use later to find Q. And so I then initialized my while loop, and I defined my internal energies, and then I found the F net with the assumption that the only force is F of gravity. So then I found the acceleration using Newton's second law, and I could from there update the velocity and position also using Newton's second law in these two lines. And so the important part of this model was to account for the actual bounce of the ball. So this was the if statement for where the position minus the radius is less than the ground. meaning the ball is touching or is being compressed once it hits the ground. And so this will change the velocity from being in the negative y direction to the positive y direction so that it continues to go back up. And then from there, I calculated the work as the F net times the ball position, and then found the internal energy using the energy principle by subtracting the work from the delta K and then the delta K and the delta gravitational from the work. And so from there I could find the new velocity adjusted with the internal energy. So this is the model versus the ball position. And as you can see, it's a pretty close representation, but the model begins to underpredict a lot towards the end here. And so there are a couple errors, or a couple reasons for this error, and one is that it could simply be a modeling error on tracker, which is shown by the inconsistency of the tracker graph itself. There could be an incorrect initial velocity because it was technically an average velocity over 2 points, and so it could be more exact. And then probably the most significant error is that I did not properly model all the energy transfer at the bounce because the ball is compressed, and when the internal energy increases, some of the energy may be transferred to the floor as it hits, caused through heat, which would actually heat up the floor. So that would need to be accounted for, as well as the compression itself of the ball rather than assuming that it hits and then bounces.